I think a good question to start off is, you personally.
Okay.
Do you remember the first time you realized biology could be engineered?
Yeah, I mean, yeah. The first time I knew we could engineer biology was when I realized that a lot of medications a lot of biological needs can be done in microbiology, like a lot of components can be made in small non-human artifacts, let's call it.
What do you mean by artifacts, I guess?
Like, the idea was that you can have a bacteria make whatever you need to make. I don't have to be stuck in the chemical room trying to all these fumes and all these chemicals to synthesize something, a small yield. You can actually genetically modify an organism and then make that organism make whatever you need to do that exists in nature, but the human body is just lacking it or needing it, or it's an alternative to whatever you need.
You can make like cells into factories kind of thing.
Yeah, you can
make them do things for you. Right?
Yes, you can.
Yeah. Cool. Where was that work when you first started doing that?
Oh, that kind of started in high school.
Really? Oh my God! In Guatemala?
Yeah.
Or in the States?
No, Guatemala, because it's like when you realize that your grandparents have a new insulin. You realize that what happened to the old insulin, and then you get curious.
So you started researching that back in high school?
Yeah, I mean, just...
You didn't do it?
No, I didn't do it, but I just started like, their insulin is different now. How is that? What changed? And then you realize, this is...
There must be something here.
There must be something here, and then you start hearing about all these other technologies that are different, and are like, things don't need that much freezing. Things don't need to be. You can keep them longer. Things are more robust and not as delicate as it was before this revolutionary happens.
So, moving a little bit forward, but like, what was something maybe in your early work, or like in your experiences, that changed how you saw medicine? Like changed how you saw the medical field? Maybe some sort of research or something like this.
What changed? I mean, I was already seeing patients that were not getting healthy, and I was already seeing, listening to stories about like,
you went to medical school, right?
Yeah,
for a little,
for a little bit, and it was like you don't, they don't have a solution. Or they're like, we'll see you in 10 years. Or you see patients, I'm coming back after my 10 years now. You're like, wait, I thought you had already this. Like, yeah, but by the way, it only lasts these many years. And so the idea was like, it has to be more long lasting than just a patch, an exchangeable patch that can be done. And then I don't have a point, I don't have a place where they was like, this is the solution, I guess. But the idea that something had to be done was there.
And then at some point you started to dive into research, like understanding research. Maybe you can tell us a little bit about that shift. Like, how did you go from medicine to more of the research side of things, and that transition of how you felt during it?
I mean, I guess the first version was a lot of these patients that need transplants, let's say, they need these drugs to immunosuppress their system. And so one of the first for research, which was an opportunity, was to see how these immunosuppressants were made. And again, it was taking that organisms and making the organism manufacture whatever you need to quiet down your immune system for a transplantation. And so this was done in mosquitoes back then. Like, we literally cut the mosquito down.
You were doing this mosquito work.
Yeah. Uh-huh. We took the salivary glands and then like removed the peptide that was being synthesized on this transgenic mosquito, and then we'll concentrate it, and then we'll go to rats, and then we'll transplant an arm or a piece of skin from one strain of a rat to another type of strain of a rat. And the only therapy they will get is this peptide that was synthesized in a mosquito.
Was that in Miami?
No, that was in Louisville.
In Louisville. Okay.
Yeah.
One of the many places.
And that was kind of like revolutionary, because then, it was like, we're impacting transplant. Mm-hmm. But at the same time, it was like, we still need to have this drug be done to you all the time. And one of the postdocs and physicians that was working with the microsurgeries, they had this idea of skin, like skin transplants that you didn't need immunotherapy, or that not only will not need immunotherapy, but they will match you. A lot of the problem with this is like you get skin from a donor that doesn't match skin color, skin elasticity. Even if you probably get back skin for the front of your face, and that type of skin is completely different. Mm-hmm, mm-hmm. And so they had this idea of like, let's figure this out, how to. And that's the first time I read about what they call the pixie dust back then, from Stephen Badilak.
Yeah.
Where he took literally extracellular matrix from pigs, intestines or pig skin, and then the powder itself was used to wound healing in skin trauma. And then you can see like, certain parts of the skin growing, certain parts of the nail growing.
Was that like your tissue engineering direction beginning?
No. The tissue engineering, it started all in Miami, I guess. Because already doing these mosquitoes and all these cells, around that time, Yamanaka published his paper on iPSCs, and the government also stopped doing embryonic research. And so what I've been working and studying all this time for at some point felt stopped, like there was no more in it, but then the next day felt like, but now there's also this. And so I wanted to understand more about these iPSCs. And the reason when people were not talking about them. Like the first conference.
Well, they're super hard to make, no?
They were hard to make.
They're still hard to make.
Yeah, there was no kits back then.
Yeah.
The first conference I went was a stem cell conference, not an iPSC conference. And even then, Yamanaka had a small room. He wasn't the keynote. The keynotes were the guys doing embryonic stem cells.
Yeah.
And so there he talks about his factors, and then he talks about like the bacteria he used to make these factors, and then he put in mammalian cells, and they were able to do, this reprogramming. And so from there I was like, well, I know how to do that. I know how to manipulate organisms to become factories of what I want, interested in them to do. And so then I was like, okay, who wants to do this, right?
You very much started like on the cell side of things.
Yeah.
Like, how can we control the cells to do things? And then I guess the iPSC stuff started getting you interested more in the human side. Like, oh wow, there's this.
Well, it was already human.
Well, maybe the other stem cell side of things was all human.
It was moving away from a therapeutic, or making a peptide, or making a hormone for the human to consume, but actually going and manipulating the human cells themselves to do it. So again, the pursuit of a permanent solution.
Like cell therapy.
Yeah. Not like, take this pill for the rest of your life. So
then how did you go to the biomaterial side of things? Like,
so that's what,
when did you first?
Well, that was Miami.
So what happened there?
I got in to try to do iPSCs. And like, hey, we have this group, and then we're trying to do iPSCs to make islet cells, or at least insulin producing cells, beta cells. And so right across from us, in the same group, in the Diabetic Research Institute, there was a group trying to do extracellular matrix to differentiate cells. So what we were doing is we were taking the exocrine part of the cells, transforming them into endocrine cells.
So using like the biomaterial to manipulate.
This was with the cell therapy. This was gene therapy.
But you were doing the gene therapy. The other group was doing the biomaterial stuff.
They were trying to do this transformation, but through environmental cues. So they introduced me to the concept of decellularization, which was like removing all the cells from. And so this now professor in Miami, he will get the hepatic trunk, which complies from the appendix to the trunk, the vascular trunk of the liver, to the vascular trunk of the pancreas, to the vascular trunk into the intestine. I mean, I'm saying it's big, but it's kind of like this size.
Yeah, of course.
And then he will chop it really precisely, and then he will grab these like kind of stem cell-like cells, or even mesenchymal cells, and he will put you go in this middle part, you go in this top part, and then days later he will come harvest them and see their genetic profile. And then he realized like there are cues, there are physical cues in this matrix like that is dictating the fate of the cells. So that's when I kind of like,
maybe there's something we can combine the two, both cells and the environment, aka
the
biomaterials, ECMs, and have those come together to make a more of a
to make an organ.
To make
and make an organ that we wanted, because he figured out that you can literally make, based on which section you cut, their fate will be switched, even if their origin was the same.
So when did you get, so we got the cells, we got the ECM, the biomaterials, where did you get exposed that potentially geometry could play a role?
Well, then I got my job with Ali K. And the job in Ali K, I got a job at Harvard with Shrike and Ali K.
No, there you go.
Literally, Shrike came.
No, come on, Ali K deserves a shout out.
Shrike literally came a month before me, out of his PhD. Me, I was just out of my undergrad. And so I got hired to do cardiac iPSCs. Like, again, there was no kits back then. Then, like, you
had to introduce the genes.
You had to
you found the recipes for.
You had to make the genes yourself. Then you had to build the vehicle, and then you had to introduce them to the cell and hope they won't become. There's really few mechanisms understood, or how to first how to turn it. Well, the mechanism to make iPSCs was understood by then. This is like 6 years in, people knew how to do iPSCs back then. But then there was also how you turn this into another cell, and change their fate, right?
To get that lineage.
Lineage. So Ali K needed, or the team, the DITRA team, the DITRA founded team needed a cardiac lineage, a liver lineage, and a lung lineage. And the liver, they didn't worry about too much because they were using primary cells for that. Same thing with the lung. But the cardiac, there's no way you can get primary cells, human primary cells. So the initial studies were like...
You became the guy.
Well, I was going to become the guy. But the cells were not there yet. Like everything I needed, you need bacteria, you need incubators for bacteria. You had
to set it up.
You need to set up a lot of these things. And that laboratory is more of a bioengineering laboratory than a microbiology laboratory. And so in the meantime, Shrike grabs me and he's like, hey, we're going to do these mechanical forces, these microfluidics. Never heard the word in my life before. First time I heard it. And then first time I saw a chip was Shrike showing me one, like, hey, this is it. I'm like, okay, I'm gonna get fired. So I literally went and read all about new, and I still have a copy of that book, like microfluidics for kids. It talks about food dyes and cool. Literally gelatin, like the gelatin you eat. Anyway, so Shrike is like, okay, and this is important because we need the cells to have a flow. Like he said, like nothing in the human body is static. Like even you might be sitting down right now, but your heart is pumping and your cells are feeling that pump. And so he's like, oh, then I understood, okay, we need these cells to grow. And so we learned about, one thing was microfluidics, and the other thing was about the architecture of the cells. Because it was not only about, a building that gets a gust of wind that is round is morally more going to be better holding their ground than one that has an angle or something like that.
Mm-hmm.
Like it depends on. I'm not going to talk architecture, but
yeah, it's a geometry problem.
There's a geometry problem that needs to be resolved for you to engineer an organ.
Mm-hmm, mm-hmm.
That's why the liver has the shape it has. Why the pancreas has the shape it has, because the geometry problem of the distribution of flow and nutrients has been solved optimally in that architecture.
Mm-hmm, mm-hmm. Is that lab, that experience where you first heard about like this word biofabrication?
Probably, yeah. Probably that was the first lab I heard the word. I mean, even then we wouldn't even call it full tissue engineering. We'll call it like cellular engineering.
Mm-hmm, mm-hmm.
Probably by for the first year, we started calling it tissue engineering.
In that lab.
That lab.
Yeah.
And then at the same time, we will be like, oh, this is a tissue engineering lab. And then literally maybe 6 months down the line, it was like, oh, this is a biofabrication lab.
So, putting that all together, what is important about this degree of biofabrication to replicate physiology? Like what is it about all those pieces that ends up allowing an engineer or scientist to replicate physiology? Like, I guess replicate the body, right? I mean,
when you study physiology, you learn about the cells' interaction with their environment, but then also how the cells, how they yield something to the environment regardless of their interaction. It's a loop. Positive or negative feedback is always a loop between what the cells feel and what the cells do, and how that comes back to the organs.
So then there's the whole side of like we've been studying tissues, cells.
Mm-hmm.
Like what are some of the challenges with that in today's ecosystem?
Oh, today's ecosystem. Ooh. One is, we need to diversify and standardize the ground where the cells are being laid on, like this material. Just as the research we did in Miami, like, you can see it in your eyes and you will say, oh, this is extracellular matrix, but there's clearly a gradient of Qs, and that gradient of Qs is not being replicated. And even when you bring it from a donor, cadaveric donor, those Qs might be a little bit manipulated because, the lifestyles we took, the age, the age differences, even the genetics underlying of ours. Some people have more collagen production, more elasticity, others don't. And so that is one. The other thing is the cell source. Even though we can make these iPSCs, there is still a Pandora's box about like why not all iPSCs work, and then not all iPSCs can make all the cell populations. Like we talk about, like they wanted a cardiac, but we were naive in the sense that we needed cardiomyocytes, we needed fibroblasts, we needed endothelial cells just for the heart. Forget about the lung, forget about the liver. Those are more cell populations. And we needed like this single iPSC to perform in that level, to be able to make all these cell types. And that's something that is still being hindered right now.
Yeah, no, I think it sounds like, well, the cell types of interest, and not just, I guess, the way we think about it today, and maybe even I think of it as like one cell type, but it's actually multiple cell types in a specific tissue. There are multiple different functions that each of those cell types are playing to be able to make the environment. Mm-hmm. And then I guess the second to that is that environment itself. So the biomaterials, the flow, maybe even some of the electrical stimulations and things like that. The other thing you always talk about is the media. The nutrients, the type of nutrients that those cells are getting, to be able to have I guess, good representation of something you're trying to study.
And that comes hand in hand with the flow too, because the first cells are gonna see maybe an overflow of nutrients coming in, while the last batch of the cells on that same flow path are gonna see a decrease in this nutrient availability, oxygen, even just the sugar that is going through. And so it plays a big role, like, you know, even in how the organ is gonna behave, you know. I mean, that maybe there is a reason why our liver is not in our feet, and then why the pancreas is where it is. That's probably also related to this gradient of nutrients or molecules being spread out from the source of the nutrients themselves. And so in the lab, to replicate that, medias are really important, because some cells live so deep inside a tissue that what they receive might be minimum but highly concentrated and really specialized compared to the ones that have the big gust of nutrients. So the big gust of nutrient cells cannot survive on a simple media, while the specialized cells might need specialized but small portions of this. So we've seen that when you put multicellular components, multi-tissue components, sometimes you might think you need a lot of complicated media, but that's when you start seeing the magic that happens inside our bodies, which is
the cells themselves are
feeding, are providing, and so you see it
interacting with each other, giving the cues.
Giving the cues. And so, but if you want to study an organ by itself, without this,
you need a
highly specialized system.
You need to kind of like substitute the entire ecosystem in that media so that it's still somewhat happy and doing its function. You
need to make sure that this environment is quote unquote healthy wise, because just like any individual that can be taken to the extreme of nutrients and be led into a non-healthy state, that can happen to the cells themselves if we overfeed them with nutrients, thinking is the best for them, but we're emulating a disease state in the cells themselves.
So we've spoken about cell types, geometry, environment, media. This is all kind of, there are other aspects, but there's this big word, NAM. Not everyone, many people are talking about NAMs. There's this whole, the FDA, Modernization Act. Maybe you can help us like break that down a little bit. Like, what is this NAMs word to you, and like, where is all this, the ideas of NAMs coming from, and what does it mean?
I mean, where it comes from, I mean, I've been doing this for a while.
Yeah, I think you've seen the evolution from, hey, you know, there's 2D cell types, we need better models. What does it mean to have a better model? Hey, maybe we need better cells. Hey, maybe we need cells with materials. Hey, maybe we need cells with geometry. But help us unpack.
What I meant when I said for a while is because when I started, when the first tetragram was given to us, the idea of a NAM was to replicate the soldier in the field.
Was it called a NAM back then?
No.
What was it called back then?
Literally was called organ on a chip.
The organ on a chip field.
I mean, the concept was already kind of out there, but it wasn't like to the level. It was more like a miniaturized bioreactors. Yep. A lot of people in the early 2000s, late 90s, were calling them bioreactors, like miniaturized bioreactors. Then the concept became of an organ on a chip, not because back then, even today, there's not a lot of electronic components. It's just because you're manufacturing this on a chip manufacturing,
a micro wafer,
in a chip manufacturing facilities. And then you can use the wafer, but then there's a lot of ways nowadays. Back then, wafer was the only way. But again, going back to what it meant, back then it meant a clone, a mimic, a twin, a physical twin of the soldiers, and that was the whole purpose, to emulate the soldier to the biggest degree to expose that to the environmental dangers.
Yep.
Get the feedback and prepare the soldier by what's going to go into the field.
Yep.
Or even if we went to the field, instead of trying to guess what was the reason of the damage or what was the cause of, run all the things and understood the feedback and know how to deal with the condition. And so it's never been about substituting the animals. Since my appreciation of the field has been always about the replicating the human condition. And by replicating the human condition, like I was back then, and it's probably still true today, is to be able to predict better outcomes, do better treatments, and achieve more precise and more concise results out of the many pharmaceuticals and many products that are being generated nowadays. Now, the field doesn't necessarily have to stop in a wet lab. That is the magic of all this. It has grown to the degree that there is liver computational models that if you give the computational biology aspect of a molecule, it will know which enzymes, which receptors, to what kinetics, which means to what pH or to what temperature will that drug work or not.
I like the in silico side of things.
Kind of in silico.
Yeah.
So that's why I do consider that this part of NAMS is also rich. Because although the resources for a computation model are really high, they are comparable to the resources that it takes to do this in a wet lab, in a bench.
So that was a little bit about like the past of maybe what you thought of NAMS, but help maybe unpack the current NAMS, recent wave of information. Like help us break it down maybe into... That's okay.
Sorry. She's probably going for more. Okay.
Help us break down the recent NAMS wave of information. Like, what is it saying? What does it mean? What is its actual implication?
Well, the one thing it's saying is that there's not a fit for all NAMS. Like, even if an institution or organization has something called human on a chip, that human system that they have generated has to be classified for a specific purpose. We are not in the level of a single system can facilitate the drug discovery or the toxicology discoveries that all industry, medical industry, or even animal industry can be satisfied with. So a lot of it was about regulation, and regulation by defining parameters and defining objectives and defining conditions of that NAM. So as I said, there's great computational ones, but that computational one has its limitations, and then we need to understand those limitations, because just like I could have run an animal study, a medication on an animal study, for example, ferrets. Ferrets are great for lung studies, lung-related diseases and all those things. If I choose to run a non-lung disease on a ferret model, I might be, toxicology or any pharmacology will tell you, you chose the wrong model for your toxicology. So by standardizing NAMS to their limitations, their objectives, and their goals, you can understand that the tool you're being used is the adequate one for your validation. And so it's really important to know that you want to do a specific target. You need to understand which specific NAM you're going to be using, and define why you're using that and what outcome was it giving you.
I guess there's a framework that's somewhat been provided, but there's actually still quite a lot of development to be done in terms of, hey, this is a good representation for this type of study.
Yeah, and it comes down, it falls down into either the institution or the organization that develop it. Like the institution that developed it can be telling me, oh, we have a heart, but what is that heart used for, right? Is that heart sensitive enough for just a heart attack simulation? Is it sensitive enough for a heart attack and an ischemia simulation, or is it just sensitive enough for toxicology?
So, so now we're moving a little bit, well, at least, into biofabricated NAMs.
Yeah.
Or we're pushing in that direction.
Yeah.
So from your perspective, what is a biofabricated NAMs? Like, what does that mean? What does those terms mean?
Yeah.
For us,
I think it means that we will be able to answer. We understand so well the field of biofabrication that for a NAMS perspective, a NAMS wave of regulation and accessibility, we will be able to generate the NAM of your need. Mm-hmm. So if you have a conversation with us and you find yourself saying, hey, look, this is my problem, this is my technology, and this is my caveat, we'll understand, like, okay, you know what? We know how to give you the answers. We know how to give you the answers to the questions that you have in this way.
And what's I guess technically novel from your perspective, this idea of something biofabricated in this way? Well,
we can tailor a lot of these things we talk with all the aspects of tissue engineering and biofabrication. We are really good at tailoring nowadays. In the sense, like, no, I know, but in the sense that we understand well that we don't have to make the healthy version for your disease model, or that maybe we need to make your healthy version for your toxicology model. We understand that we have the tools and the knowledge to manipulate this with the same cells. So, or we can do the other way around. We can manipulate the cells to remodel a scaffolding that we have engineered. At the same time, if we want to just imply physical forces, we are really good at implicating, high stress, low oxygen, high temperatures, conditions that people with hypertension, with oxygen limitations, mm-hmm. or individuals with different vascular or cardiovascular or lung-related conditions, hypertension conditions, will have, mm-hmm. because these are physical forces that are really affecting. And we are really good at simulating that physically, biochemically, or just by changing the microenvironment of the engineering.
Bringing together, it sounds like a lot of those pieces that kind of like been learning over the years in mm-hmm. terms of the cells, the cell type, the microenvironment with the biomaterials, the patterning of those cells, mm-hmm. so you can get better representation, and maybe even to a degree the influence of flow, mm-hmm. Or pressure, and then also the considerations of the media. And so bringing all that together, mm-hmm. using our tools, whether it's 3D printing, mm-hmm. bioreactor, bringing all that together.
At the current stage, we're not going to be able to print everything at once.
Yeah.
But what we bring together is we understand those limitations, and we understand the best way to print a bioreactor, the best way to print the tissue engineering, biofabricate the tissue engineering component, fabricate the mechanical and the environmental Q component, and then biofabricate by putting all these individual pieces together.
Yep. Mm-hmm.
And that's how we circle down every aspect of the mechanics, the chemistry, the biochemistry, the physiologics, and to be able to replicate either pathophysiological or pharmacokinetical studies.
So what do you think, like, the industry looks like? This NAMS modeling, complex tissues, microphysiological systems. Mm-hmm. What does it look like over the next maybe 3-5 years? Where do you see it developing?
It will fill the gaps where drugs or the pharmaceuticals have seen their products failed. It's not going to completely disrupt the platform. It's not going to stop doing the high throughputs, the library developments. It's just going to see if there's a level of investment carried out on a specific molecule, a specific therapeutic, and then they find themselves on a gap that their own gut tells them it's going to work,
sure.
and all the data points out that it's going to work, and then they just see that it's not passing the hurdle for the next stage for commercialization. They will go back and understand that in order for them to ask this question and they risk the possibility of failure in the market is to use a NAM.
Yeah, so it sounds like it'll become like an additional layer, an additional area of validation potentially, in maybe a large degree, or maybe it sounds like initially where they think that they need more data, and this is going to play a role in helping them create more data that helps them decide what direction to take with their...
Yeah, most importantly, that data is going to be human-related data, humanized data. So it's not about making a NAM with synthetics or full synthetics, or it's not making a NAM with animal components or any other type of non-human component. It doesn't exist inside of what it will be a human body.
Yep.
It's about de-risking a patient. So instead of going into the field and using the patients as guinea pigs, we will actually have human guinea pigs.
Yeah.
In that sense of an understanding the precise lack of gap in their knowledge of data that I need to fill that is fully human-based or human-directed.
Totally. Yeah. Cool. So, what keeps you motivated doing this work?
I don't know. I like it. No, I mean, if you want to see it done, it's going full circle about like making an organ, right? Like I tell you, some of these patients came back and it's like, oh, we're gonna need something again in a couple of years, and why? Because my organ, my tissue, my body is not doing what I need it to do, and at the end of the day, it's like. Maybe my future generation will take it for granted just reprinting an organ, but it's building these mini organs or medium-sized organs or the first trials of organs that will lead us to becoming the standard, gold standard in any therapeutic, in any type of level. But in the meantime, I can say, oh, I know how to make an organ. I'm not going to implant that organ on you, but I'm pretty sure that these cues, this checklist of this is what you need to make an organ.
Yeah.
We are refining that checklist, and that's what brings me home every day. That brings me out of home, brings to work every day.
No, it's an interesting point. I think a lot of these past maybe 10, 15 years, we've all continued to say about, oh, we're going to make organs, and I think previously our headspace was a little bit like, oh, okay, we're going to make this big chunky tissue that's going to go in someone and be implanted, and remember the videos of like a Tala or the Langer ear or the Conti skin, that kind of stuff. And I think now, after all of this science and engineering and biology, I think we're probably getting more towards the point of thinking of like, well, we can probably build these like micro tissues that actually have some sort of therapeutic benefit. Well, one's from a modeling side, but potentially even from an implantable side. I think that probably gets us closer to saying we're building organs. I mean, it's just a certain cell type that does a certain function. That in itself, it's doing one piece of a larger organ, and I think that probably certainly keeps us excited in terms of the industry. I think what's something you've learned from working at the intersection of biology and engineering?
Oh my God, that Mother Nature is wise. Yeah, Mother Nature is wise and Father Time is just a bastard. No, I mean, there's always, if you talk to some cardiologists, they'll be like, Mother Nature made a problem here, made a mess here. if you talk to IT people and they see the whole subclavial branches, they'll be like, there's a wire managing problem with Mother Nature. But then the moment one of those fails, it just comes to. So they, biology knew what knows what to build and knows how to build it. And, when you now try to build what nature has built, you realize that it all makes sense. When you see it from afar, when you don't understand it too much, you just like, oh, this is a mess. Why is it like this? It's ugly.
Yeah.
But when you try to do it yourself with your own hands, with your own work, with your own materials, putting your money where your mouth is, that's when you realize, like, this is the best way to do it.
Yeah.
There's no other way to do it. Even though there is another way, I'll tell you that, because a fly has a heart, doesn't look like our heart.
Yeah.
But that heart is for the fly.
Yeah.
Yeah, and there's a reason why, even if you have a pig heart, yeah, it can work to a degree because there's proximities to it, there's relationships to it. But at the end of the day, a human heart will be a human heart compared to a pig heart being a pig
totally.
heart. And the reason about the father time is because everything needs to mature. Once we tackle that matureness, that extra 4D component of our 3D world, which is time, then we can and again, it comes down to the iPSCs. If you can get an iPSC to become what you need in a faster way, you have a better tissue engineering aspect.
Totally. I think the 2 points to that I really have enjoyed myself is that, like, when you always don't have to, you have to get the cells close enough to allow them to work with them. As the cells have cues, they have instinct, they have a way of reorganizing themselves and doing work, like you said initially with the factories. And so being able to guide them, give them a good environment, empower them, that they end up doing their own reorganization. The cells are smart. They're going to go off, and if you give them the right empowerment, they're going to do amazing things. And it's awesome to see, like, under the microscope, for example, you're seeing like cells reorganize in real time. And then I think, probably a whole portion of this on the father time side of things and the maturing, it's like, and I think that's been one of the challenges with cost. It's like, I'm always a proponent of the body as a bioreactor. So how do you get the cells close enough to that? Then you can use the body as a bioreactor, or if we're studying those cells in the dish, then how do we think about giving them the right cues so that they go off, and as they empowered, end up reorganizing in the right way so that they give us experiments that give us good data. So. What advice would you give to someone entering this field today?
No, because I have some couple mentors nowadays, like young high school guys, and it comes down to, like, there's so much to learn, but you have to be patient and all that. You need to learn all this, you need to learn the physics, you need to learn the chemistries, and at the same time, as you learn it, don't expect to be an expert on this is a team effort. It's just you and I right now, but every single thing behind us, even we have an army behind ourselves. And it won't be just a single mad scientist like Dr. Frankenstein, and maybe his ego, they're trying to build his monster, but in reality, you have an army of different degrees of engineers, physicians, chemists, biologists, and all the different things, just being in concordance in an orchestrated way to build the organ, right?
Yep.
Again, that's why, Mother Nature was able to do it, and it's just like, wow.
Yeah, no, it's always humbling.
So to the young ones, it'd be like, learn as much as you can, but also understand, learn to collaborate, learn to be a team player, and then, to be honest, that's it. And then at the end of the day, I guess it's all imagination, because we all grew up reading Jules Verne and all these other like futuristic books, but there's really few books out there before that will tell you, let's build an organ, or let's 3D print, let's make this blob become something functional. Life was still being considered like quite delicate.
Yeah.
Then nowadays you have more of those books reading about like, oh, I just made an arm for myself.
Yeah.
But when I grew
different TV shows.
yeah, different TV shows, Westworld.
Yeah, there you go.
But even then, the classic futuristic ones, nobody was talking about. Yeah, they were talking about going to space. They were talking about like under the sea. They were talking about like speed of light, the physical stuff. But nobody was saying like, oh, I need a new eye. Give me a new eye, right? We were still relying on the fairy godmother to come and give us a new eye.
Yeah.
Or get our arm back.
Yeah.
Make Pinocchio a real thing.
The field is young, and even the imagination of the field is young, for sure.
Yeah, so if you are a young guy and you have a lot of imagination, like I think a lot of us did, that's rich,
Yeah. Cool. Well, thanks so much for sharing your thoughts with.
Oh my God, with you.
Yeah. That was a conversation with Julio, our co-founder, colleague, and friend, diving more into the world of tissue modeling. We are excited to be launching biofabricated NAMs, and if you're interested in working together, feel free to reach out on our website. We'd love to speak with you. Until next time.